Hi again. Sorry, brief pause. Yeah, so now this is a closed system. It's not particularly interesting, but what would you do if you wanted this to keep going? You want to keep powering your light bulb for forever, right? Well, the obvious way to do that is to punch a hole in this tank, right, so water can keep flowing out, and put a hose in on this one and run water in. And, you can get that done. A system like this, right? So long as you're running water into it, and water can go out, this water can always be moving towards a more stable configuration. It can be going towards equilibrium, but it never gets there, right? It's moving towards equilibrium, doesn't get there because it's an open system, but as this is moving towards equilibrium, it's able to do useful work. And this can happen in multi-steps. But you have something like this. Again, working towards equilibrium, but it doesn't get there. This requires input, right? So there's energy, well, for our analogy, there's energy coming in here in the form of water, but that things are coming in, things are going out. Now, it's a common misconception that equilibrium, the products and the reactants have to be the same on both sides. That's not the case. At equilibrium, you just need there to be no net work produced. So, just to beat this, is kind of a subtle point, but it doesn't matter how big this tank is on this side or on this side. They don't have to be equal-sized tanks. Once there's no work able to be performed, that's when you're at equilibrium, right? It doesn't mean that everything suddenly freezes. It's not like this water doesn't still experience molecular motion, right? Like, there's still molecular motion happening and stuff, but there's no useful work able to be performed. Fair enough? Now, cells are not in equilibrium. They're open systems, so they're experiencing material flowing in, and that's good. Equilibrium is not the same thing as homeostasis. Equilibrium is... Sorry, I need to check my settings here. My computer is making me worry. Partially because it cut out this morning. Hi, okay. When cells are completely at equilibrium with their surroundings, they're dead. You don't want cells to be completely at equilibrium. So, not equilibrium, but reactions are still going to be moving towards it, right? So, excuse me. Sorry. A couple terms just to know. Exergonic reactions are reactions with a net release of free energy. They're spontaneous. You can think of like explosion, right? Gonna release free energy. You don't have to put any energy in to make it happen. An endergonic reaction requires free energy from its surroundings. It's non-spontaneous. You have to pay for it. So, examples here, right? So, either of these are possible, right? But in an exergonic reaction, you've got the reactants that are really high in energy here. As the reaction takes place, energy is given off, and the products then are in lower energy. This is the idea of a ball being really high up on a cliff. It's unstable. It's high in free energy. As the reaction takes place, as the ball falls off the cliff, energy is given off. You can use it to power a turbine or something, right? Energy is given off. The ball, at the end of the day, is in a much lower energy position than it was before. And you can see that the energy release, this change in free energy, there's a negative delta G. This shows you that this is a spontaneous reaction. Now, it's entirely possible to have reactions that are non-spontaneous. You just have to pay for them. So if you're going to put the ball from the forest floor up to the top of the cliff, you have to put energy in. So if the reactants start low in energy, and then end much higher in energy, it's a non-spontaneous process, and you can see that with the energy's been added in. This has a delta G that's positive. A couple examples here. You can see that like this little guy on the diving board is at a higher energy state when he's up there. it's an unstable system. There's greater capacity for work. Once he's hit the water, it's a more stable configuration. Less work's able to be done, and there's a lower free energy. Same thing for something like this. Like if you start with a whole bunch of little dimolecules in a clump, it's a spontaneous process to have diffusion happen and to have it just like go out. If you're going to go from a whole bunch of scattered particles and put them back together, that would require energy. So this is higher in free energy, this is lower in free energy. So to go from this ordered system to this less ordered system is a spontaneous process, but to run it the other way is a non-spontaneous process. Similarly, we see this molecule here. It's nice and organized. As the chemical reaction happens, that's spontaneous. It breaks it into less organized pieces, all this carbon dioxide and water. To put these back together would require energy. Yeah, fair enough? Now, all these things, great, we're either giving off energy or getting energy, that's beautiful. The important point is the cell is going to be doing a bunch of reactions, and the cell needs to do work. The cell is going to do three main kinds of work. It's going to do some chemical work, whether that's constructing something or have certain reactions happening, that kind of thing. It's going to do transport work, things like having carrier proteins that that move particles across the membrane. You can have pumps that are moving things across membranes. You can have something like endocytosis or exocytosis. You can be doing transport work. And then there's also mechanical work that the cell can do. So you can imagine, say, a muscle cell that's going to be contracting, or you could think of like a flagellum cell that's going to be physically moving. Now, to do all these things, the cells are going to need energy, and typically the form of energy the cell's going to be using is held by the molecule ATP. So I think a lot of people have heard of ATP. Often sports people have heard of ATP. The cell uses it. The classic analogy is the currency of energy. This molecule, adenosine triphosphate, looks like this. It's got this adenosine part, this sugar, and this adenine part. That's nice, but what we really care about is this triphosphate group. So I hope you remember from before that like charges are not stable next to each other. So all these phosphates next to each other are very unstable. They're very high free energy. This is the idea of having a ball really high up on a shelf. Nothing's happening quite yet, but if something happens, there's a lot of free energy to give off. ATP, the A comes from the adenine portion. The TP stands for triphosphate. If this ever only has two phosphates, it's ADP, diphosphate. And if it has one, it's AMP, monophosphate. But we're expecting to see it as ATP and ADP most often. So what this looks like is we've got this triphosphate group, right? And there's a lot of free energy. This is a high energy molecule. With the addition of water, this bond can be broken, and you can end up with inorganic phosphate and ADP. As that happens, it goes from a high energy state, high free energy, to lower free energy. So you give off energy. Just to be clear, it's not like there's a little unit blob of energy sitting in this bond, and once you snap the bond open, you have a packet of energy. You can think of it that way, but that's not exactly what's happening. You're going from a less stable, high energy configuration to a more stable, lower free energy configuration, and you get free energy off when you do that. So this can be used to power work, which is important. um, this slide and this slide are just for your study. We're going to walk through it here, okay? So this reaction right here, where we've got glutamic acid and ammonia coming together to make glutamine, it's an important reaction. You need this to happen. But it's non-spontaneous. Can you see why it's non-spontaneous? Here we can see this delta G, this change in free energy. That's a positive number, 3.4 kilocalories per mole. That's saying it takes a certain amount of energy to have this reaction happen. So it's not spontaneous. Excuse me. It's not happening on its own. All right? But there's got to be some way to pay for this, right? You need to make this happen. So the way you do that is you couple it. You can couple this reaction in this way. So you've got glutamic acid with ATP, and you can make it so that these react, and this now is called a phosphorylated intermediate. It stole one of the phosphates here, and this is now ADP. And then this phosphorylated intermediate interacts with ammonium, and you end up with your glutamine and your ADP plus inorganic phosphate. So the deal is, going from ATP to ADP and inorganic phosphate is a spontaneous process. The stuff, it's not like it explodes, but as it breaks down, it gives off a lot of energy. And we can see that it's a spontaneous process. Its change in free energy is here, this negative 7.3. That's pretty impressive, right? So it's giving off energy. It's going from high free energy to low free energy. This one is going from low free energy to higher. It's costing something. But if you sum the entire reaction, you can see that the magnitude of this negative free energy change is greater than the magnitude of this positive free energy change. So this overall coupled reaction is still negative 3.9 kilocalories per mole. So this now is spontaneous. You've coupled a non-spontaneous process with a spontaneous process. You've basically told ATP, all right, we can get you to a lower free energy spot, but we need this reaction to be run through it. You can think of it like this picture here, where you want something non-spontaneous to happen. Say you want this turbine to be spun and this light bulb to be powered, right? So you stuff that portion of the reaction right in the middle of this spontaneous process that's happening, so that as the spontaneous process happens, it drives this. And that's what you've done here with ATP. This ATP going to ADP and inorganic phosphate has to go through in this metabolic pathway that's been set up, has to can't happen until this phosphorylated intermediate and this ammonia have been combined like this. So basically you can use the energy that you get from the spontaneous process occurring to drive non-spontaneous processes. I think that's for many people that's fairly intuitive, that you can basically, you're buying the energy, not really. For some people it's a struggle. Your book actually has a pretty decent explanation of it. So that's where we are with this so far. I hope it's making sense. I hope it's good. This kind of thing can happen for a bunch of things. So this is some sort of chemical work that's being shown, right? Chemicals being combined in a certain way. You can also have transport work. So, for instance, this little transport protein is actively pumping particles against its concentration gradient, right? So, left to their own devices, these solutes would like to be the other way, right? They'd go down the concentration gradients. That would be a spontaneous process. This non-spontaneous process that takes ATP energy, right? Takes energy from ATP. You can phosphorylate this. You can drive the the transport of solutes. You could also do some sort of mechanical work, like moving vesicles around. Excuse me, I'm sorry, I'm really tired, and I realize you probably are too, so hang in there, it's all good. You can drive mechanical work with this process as well. Hopefully that goes well. Great. Okay, so that's the main points of the idea so far, but we've got a little bit more. So ATP, we've seen it goes from ATP to ADP, and inorganic phosphate. That happens a lot. It happens in this pattern. So we have ATP. In the presence of water, it can be broken down into ADP and inorganic phosphate, right? This ATP, you can break it. As you break it into these two components, you give off energy, right? And so this energy is typically used to drive cellular processes, right? It's used to do something. It's harnessed. Then you have all this ADP and inorganic phosphate. So you want to go back to having ATP, right? Because this is what the cell can actually use and break up to do stuff. In order to put these back together, you have to put energy in. So you put energy in, often from, say, like, we'll get to it next week, but as you, say, eat sugar, right? You can put energy into the system. As you put energy into the system, you can snap these back together. It costs energy to put these back together, and then when you break this bond, you can release free energy. Yeah? I hope that's going okay. So that's the overall where we got to today. We spent a long time talking about equilibrium in class. I also started just briefly onto the next concept. It's hugely important for metabolism, but we'll spend all of Friday talking about it, though I'd like to just start right now because otherwise we're going to run out of time on Friday. So that's the concept of enzymes. So we have all these metabolic processes happening, right? So whether it's this kind of thing happening, these chemical reactions, they're happening, there's energy involved, there's, doesn't have to be, but things are coming together, things being broken apart. Oh, just for the record, is everyone comfortable with the things that you have at the beginning? Those are called the reactants. And then at the end, whatever you make is called the product. So if you have thing A and thing B, and you have some sort of reaction happen, and then they come together and form thing C, those original A and B portions are the reactants. The C thing is the product. You could also run it the other way. If you start with thing C as the reactant, and then have some chemical processes, and you break it apart into little bits, the parts you broke it apart into are then the products, right? So knowing about the delta G of a given reaction is good. It can show you if it's spontaneous or non-spontaneous. What it can't show you is how fast it goes. It can't do anything like that. It just shows whether it's spontaneous or non-spontaneous. Lots of spontaneous processes take a really, really long time to happen, or they're very unlikely to have happened. For these to occur in any meaningful biological time frame, catalysts are used. Now, catalysts are just things that speed up a reaction, but aren't actually consumed by the action. So, for a dumb example, if you're cracking walnuts, right? Using a nutcracker speeds up the walnut cracking process, but it's not like you use up the nutcracker when you crack a walnut. It's not broken by doing this. It's not hurt from doing this. It's still around. You can just crack nuts indefinitely, right? So enzymes are going to speed up chemical reactions. They don't get used by the reaction, and when there's proteins, where's my mouse? Proteins that act as catalysts are called enzymes. We're just going to see this picture here, and then we'll pick back up from here on Friday. this is the picture. We've got this molecule here, whatever it is. It's got A attached to B, right? We've got this molecule here, C attached to D, and they're all in somewhat high free energy. Not like terribly high, but there's somewhat high energy, right? That's where it starts. The whole system would be more stable if A was attached to C and B was attached to D, right? So this is a much more stable configuration. There's a negative G here, so they're going from here to here is lower in energy, right? So this is a spontaneous process, right? This gives off energy when you do it. There's some amount of energy here that's given off. Higher energy, lower energy. Less stable, more stable. This whole thing's spontaneous. The problem is, and this is just where we're going to end, this is worth thinking about. The problem is, to get from A and B to A with C, this bond has to break first. Or to get C and A or D and B, this bond has to break first. Now, the place that these molecules are at right now isn't super stable, but it's not terrible. Yes, the position over here is better, but to get there, this molecule has to break up first. And to do that, it's extremely unstable. That breaking up when it's not actually attached to anything else is really, really unstable. You can imagine maybe there's like a partial negative charge somewhere here and a partial positive charge here, and right now those are kind of being balanced out beautifully. When this breaks up, this one has to handle the partial negative charge all by itself, and this one has to handle the partial positive charge all by itself, or whatever. And that's very unstable. So to get from here to here, it's a spontaneous process, but there's something in the way, this transition state that's really high in free energy. And we'll pick back up there on Friday. I realized this was pretty short. We did spend a fair bit of time on the exam and also on an example. If you have questions about the exam, please do email me. I do appreciate that. And yeah, we'll talk about enzymes more on Friday. Bye.